Hey everyone, welcome back to making a Python 3 NES emulator. My name is Andy and I'm just gonna continue going on with what we've been doing recently, which is coding this thing in Scratch for a NES emulator. What we've been working on recently has been the instruction code, so implementing the CPU part of it, and we're basically just going to continue doing that today. Not much really is going to be different, just going to be more work and more instructions. So the way that we're going to do that is through using the NesTest ROM, which is a pretty cool way of testing all the instructions on the 6502 CPU. And yeah, we've been getting some comments about how to do this from Danny, and he has left another comment and another thing over here. I'm echoing. Which is just going to explain some things. So what we were doing last time was finding all the instructions and putting them into a dictionary so we can interpret them. Does this need to be done on every ROM load? No, it definitely does not. So we are just going to get rid of that and put that into the CPU initialization code. And then we're going to continue working on some of the instructions. Cool, so let's jump back to some code and start hammering away. So this is kind of what we're talking about here. Only needs to be done when the CPU is created. So let's just do it. So we want to be creating the instructions that the CPU can interpret. And the way that we do this is by iterating over this instruction-based class and finding anything that can inherit from this and turning that into an instruction that we can read. Cool, so what do we want to do? We want to make a self.instructions and then just access that later on, because now everything is stored in the dictionary, and now every time we load a ROM in, we don't need to reload the instructions. Now obviously this will need to become a self.instructions. Cool. Alright, what's going on next? What? A few more things. So probably the first thing that we're going to go back to doing is doing instructions. And the what we kind of were stuck on last time was how to increase the stack pointer while we were doing this JSR instruction, and so how much it needs to include and how we store multi-byte values into something. So I'm just going to quickly go back and say that we've probably addressed this. I don't know if there's a add your reaction. Heart. Perfect. Alright, so we'll leave a heart for that. Mark that as resolved, I guess. And Danny was just saying, a little skeptical about mix-ins. Yep, it's fair enough. I'm also skeptical, but I just wanted to try out and see what happened. I've got a few takes in mind for his Chip 8 emulator, then back to the NES emulator he's working on, which is super cool. And that runs in the browser now, and I've played around with that. It's pretty nice. So be prepared, we're going to have to do some illegal instructions. Yeah, we knew that. At the end of the vid, you're working on pushing the PC to the stack. You're shifting through 8 and 16, but it should be 8 and 0 since you're throwing away the lower 8 bytes. If you need to truncate it, yeah, okay. Right, so we're going to need to do some of this truncation stuff at some point. We kind of knew that. So let's just do it. Yeah, alright. Well, we can start off by increasing the size of the stack. We can start off by, I've kind of always wanted to make this a helper method, so instead of getting the memory owner and then setting it. So the reason that we do this is to do a bit of memory indirection, or what's the term I'm looking for? Memory mirroring, basically. Memory mapping. So instead of doing that, let's just have a, well, we'll also do that, but let's have a set memory function, which is just going to do that for us automatically. And it's going to return none. Sets the memory at a location to a value. And value should also be an int, I do believe. Oh yeah, from white space. So we're using function annotations, Python 3 function annotations, which is kind of our standard thing. So get memory and then set, now believe, yeah. Cool. So let's just do that. So this is the code that we kind of want to copy across here, which says the memory owner is going to be the memory owner of the location, and then we want to set that memory owner's location to be the value. Now the memory owner will take care of offsetting its address. So if it starts at 8000 and we pass it in set byte 8000, it'll know to minus 8000 from that and just set it as 8-bit. Cool, so the write function can now just be CPU.setMemory memory address value. That just makes our lives a bit easier. And then when we're doing that in our jump register as well, we can do the same thing. So memory owner, CPU.setMemory for that memory address and to that value. Now here's an interesting one. We want it to set 2 bytes. So we might need to make this accept an optional parameter, which is the number of bytes that it's setting. It's going to be an int, and it's going to equal 2. God, how does this syntax work? That's horrible. Anyway, and that's going to set the number of bytes. Yeah, that looks pretty much nice, I think. Cool, so now we want to set the memory from the memory address to the value, and we know that it's number of bytes. We're going to use name parameters here, just because it's a bit more explicit about what that 2 is doing, which I think is kind of nice. So let's keep that convention up. We can do if we do this in Python 3, it just leads to a parameter that's only keyword available. So you can't call it with just the naked 2 now, you've got to call it by its keyword. Which I kind of like. I don't know, I won't do it for now, but I might come back and do it later if I ever screw up with it. Basically. Alright. So we're setting the memory and then we want to increase the size of the stack. So this is kind of where we got to last time. Set takes 3 positional arguments, but 4 were given. Yeah, well, it will... What? Set location value number of bytes. That's weird. Location value number of bytes. Am I calling it on a memory owner? Position int value size. Huh. Ah. So it's at another location. We're calling it with something. So value is none that we're trying to set it with. That's really weird. Probably shouldn't be none. Okay, so where is that getting called from? That's probably getting called from here, right? So this value is probably none. Value, none. Okay. So we want to store the PC reg on the stack, and the reason that value is none have I done something? Store the PC reg on the stack. So really, it should just be cpu.pcreg. If I open up my source control, is that something that I accidentally changed? Ah, yeah, it is. Okay, so we were ignoring the CPU, the memory address and the value that were being passed in, and we were just calling cpu.reg and pcreg. That makes a lot of sense. cpu.spreg. So what we actually want to do here is store it at the position of the stack. The stack pointer is 253. And we want to store the PC reg, which is going to be 50,688. What is the memory address that is getting passed in here? What is a jump? Jump is a type of instruction. So the memory address is going to be class.getAddress, which should just return none. I would have thought. Okay. Let's go back to here until we find our JSR absolute. Yeah, so what's the memory address? 50,000. Oh, that's not right. Okay. How are we getting that value? It's calling it of absolute addressing. Huh. Why is it calling absolute addressing? Oh, because right. Because I'm not actually calling this base instruction. I'm calling. It's actually a jump JSR absolute, which uses absolute addressing. Holy crap! All right. So why does it jump absolute? So jump absolute doesn't actually use absolute addressing. It's just. Ah, sorry. We're on JSR. A JSR doesn't actually use addressing unless I'm wrong. Let's go check that out. So JSR pushes the address -1 of the next instruction onto the stack before jumping. Right, okay. I know what's going on. So the value that we get passed in is the value we want to jump to, and then we want to write the value of the PC reg, so where the current execution is, to the stack before we do that jump. Yeah, okay. That's my bad. So what we're saying is that the stack pointer, let's go back to there. cpu.spreg is 253. So should the stack go up or should the stack go down? Let's look at the NES Dev Wiki, NES reference guide, and we'll probably want to be looking at the CPU, I suppose. Potentially we kind of also want to be looking at the, I don't know, RAM or something. I guess that would be part of the CPU. So the instructions, I don't think there's going to be anything here that's going to be useful to us. No, addressing modes, memory map. Memory map is probably going to be useful. So we have 2 kilobytes of internal RAM. We have a stack pointer that starts at FD, I believe. And so if it starts at FD, that makes it unlikely that it's going to count up, right? Because we can only store a single byte. So if we can only store a single byte in the stack pointer, and it's almost starting at the top, we really want it to be counting down. Yeah. Okay. So increases the size of the stack by going negative. Now, I might actually write some helper functions to do this because I feel like this is going to confuse me later. So let's go back and do a bit of cleaning up. The other thing I want to do is make some of these functions private, just to kind of remind myself how to access things. So this should become get memory owner, and set memory is fine. Find instructions is probably a private thing. Honestly, I'm going to move it as well, just because it doesn't really need to be there. Start up, get memory, right, rock on, set memory. So what was the other thing we want to do? So heap management. Now, or stack management, I should say. Gonna confuse those terms from every now and then, but when I say stack, I mean heap. Instead of doing this, do we want a stack object? No. For now, we're just gonna do it. So let's say increase stack size and a size, which is going to be an int. So how much do we want to increase the stack size by? And the answer is increases the stack size by decreasing the stack pointer. Nice. So self.spreg minus equals size. Oh, semicolons. Whoops. So CPU dot increase stack size by 2. And since this number of bytes is actually just going to depend on the size of the PC reg, isn't it? Because what is the PC reg currently set to? 50,000. Ah, shit. How can the PC reg? I think actually the NES has a 16-bit address buffer, which probably means it's got to have a 2-byte PC reg, which is why when we're storing anything to do with the PC reg, it's going to have to be 2 bytes. I could be making that up completely, but that kind of makes sense to me. Alright, and then we want to jump to the memory location that we've done. Alright, so this looks better to me. The other thing that we're going to have to do is go to where we actually write the value, which is here. We need to make sure that if we're writing a multiple bit value, we're doing it correctly, which we're definitely not doing here. So this was the comment that Danny was leaving, was that this wasn't right. I think. Anyway, let's keep going. Missing white space. Yeah, okay. So I believe that we're shifting by 8 and 16, and what Danny was saying was we probably should be shifting by 8 and 1. And that probably we should create a helper function to do this because we're going to be doing this a lot. So let's create a helpers file. And let's do int to byte. Now, we're not actually going to convert it to a byte. So this is going to be a bit misleading, but what we kind of want it to do is cast it, so to overlap. So cast a single int to a byte, and basically we just want it to return that value mod by 256, which is going to get it between 0 and 255. Mod 256. So that's fine. Now I believe what the other thing that we wanted to do was yeah, this is what Danny is doing, is 2 bytes, yeah, sure. New byte, value shifted by 8, and then the next value, right? You'll need to truncate it though, cast, or with 0xf. So I believe that modding with 256 should also do this, but it might be slow. It might be smarter to bitwise OR it with 0xff. But for now, we'll just kind of presume that what we've done has some level of sanity. We'll keep going. Maybe, yeah, sure. Yeah. From bytes by 1 by 2. Right, so since it's a short, which is 2 bytes, we need something that will convert it to multiple bytes. Ugh, yeah, okay. So we kind of actually just want something that converts it to multiple ints, because we deal with ints, not bytes everywhere. We're kind of just praying that nothing overflows, because we don't really have a concept of a short in Python. Yeah. Alright, so let's do short to byte. Let's create our own. We could just roll our own short class, to be honest. That might even be the smartest way of doing it. Which would be crazy. Yeah, I'm pretty tempted to do that. Oh. So let's say that we get passed in a value. So here we're casting a short to 2 ints. Represent, yeah, 2 ints. Sure. Now it says to byte. We're not actually returning bytes, so we're just returning ints that have been truncated. Yeah, okay, whatever. We'll come back to this naming convention later if we need to. So, because it's a short, we actually want to do what Danny was doing here, which is going to be to bit shifting, and then, so bit shifting by 8, the top value, and then bit shifting, not bit shifting the next thing. So, we really want to be doing return, and we'll say, so upper is going to be value bit shifted by 8, no, bit shifted that way by 8. And lower is going to just equal the value. And then we actually just want to truncate both of these. So we actually want to just call int to byte, jeez, on these and ensure that they're truncated. Cast a short to 2 ints. So we actually kind of want to return upper lower. Is this how he's doing it? He's casting back. Yeah, he's passing back a new array. Okay. Yeah. I'm hoping this mod 256 works. I hope this is the mod operator in Python. That'd be awkward. Well, we'll find out, I suppose. Yeah, let's see. Let's see what happens when we try to set the memory with 2. So let's just breakpoint here. And step into that. Get the location, then we want to set it. So we're not calling that code yet. Right. So instead of doing this set thing, we could just do a this is horrible, but if size is going to equal 1, then we just want to set the value. I'm sure there's a much better way of doing this. if size equals 2. Now, is there going to be anything other than what we do here? Anything other than shorts? Probably not. Maybe. Oh, let's see. No harm in trying, basically. For I in range size, self.memory get position. Whoa. Right. So instead of doing this, let's just get our bytes. So upper, lower, I believe was the format we agreed on. Yep. Upper, lower equals short to byte. And I should say this is going to return a list of ints. Again, this is the typing library syntax. And this is just going to return a single int. Short to byte, so let's do that of our value. And then we just kind of want to do a double write. Whoop. Whoa. This is not what I wanted to be doing. Alright. Lower. So we start at this memory position, and so we kind of want to write at the lowest at this location, and then one up the stack. Where up the stack is going to be -1. We want to be writing the lower value. Now we might have to flip these at some point, depending on how Endianness occurs when we're reading the stack. I don't know, but this seems around right to me. So let's see what happens if I breakpoint here. Upper, lower, both 0. Alright, what is value? Does this seem right to us? Value is 0. Where is this getting called from? Instruction is stx0 page. Why is that calling this? Oh, number of bytes equals 2. Oh, that's a bug. Number of bytes equals 1. Alright. Yeah. Bugs. Cool. Now a number of bytes equals 2. There's got to be a nice way of doing this, but whatever. Instead of all these 1s and 2s everywhere, I probably want to put in like a enum that defines them as shorts or something. So I'm going to do that. In fact, I'm pretty tempted to do that right now before I forget. So class, these are really numbers. I don't know what they're called in C++. Yeah, whatever. Numbers is going to be an enum. So Python 3 we have enums. So let's do byte equals 1, short equals 2. So now we say int to byte and then short to byte. Yeah, that kind of seems consistent. Yeah, sure. They're not really, yeah, going back to bytes. Oh. So if size equals numbers dot byte, and if it equals numbers dot short. I should probably make this an else if. Alright. Cool. So now we have different functionality depending on whether we're writing a byte or a short, but that's kind of fine, I think. Potentially which way we write might depend later on. And we're probably going to want something that casts from, well, we know we are eventually. It's going to be byte to int, which is actually just going to be a value int. And return an int. God. So cast a single byte to an int. Now this doesn't actually need to exist. Yeah, that's true. This doesn't need to exist. This really should say short to bytes. I think this makes it much more clearer. But we definitely need bytes to short, which is going to take in upper, lower. These are both going to be ints. And it's going to return a single int. And it's going to cast two ints to a short. So it's going to return. So if we've got two ints, we kind of just want to combine them, probably by bit shifting, right? So it's just going to be upper shifted plus lower. What are the odds that that's around right? Binary OR. Yeah, now this, that's a great point. This might need to change depending on whether we want to shift lower or upper. Not sure. We're going to write some test code around that. Alright, so where are we? Self-dog and memory. Alright, what's upper? So what's that value? 50,688. So let's do some thinking about whether this seems around right. So the value is 50,688. So if we do hex of 50,688, we can see it's 0C600. So we'd think if we were going to store it in bytes, they would store C6 in one and 00 in the other. Maybe I'm wrong about that. So let's see, what's the lower going to be? The lower is 0, which is what we expect, and the upper is 198. Now if we turn that into hex, that should equal C6. Sweet, it does. So that's right. Now, are we storing these in the right order? We don't know what the right order is, but let's just think about it. So upper is going to be C6. So we're going to store that at, yeah, technically, this is closer to the top of the stack, and this is further down the stack, which is, so the stack is actually starting at the top and coming down. So yeah, that makes sense. So if we looked at it, kind of in a way that makes sense to me. Let me just plug this in. That's a bit loud. Pro membership. Sure. So we will have our stack. So it starts at FD, and then we're going to be counting down all the way down to 0 presumably. So our pointer starts here, and then we're going to start filling this in with values. So in this case we're putting in C6 up here, 0, 0 down here, and then our FD is now going to point to here, which has nothing in it yet. Yeah, so this is the upper part, and this is the lower. Now what we've actually done as well is we've stored the value of this FD in the PC reg. We stored the value of this is the value of the PC reg to come back to. But this will now be down to FB. The stack register also gets updated. I suppose is the point. Alright. Save that. Yeah, I mean, this looks around right. I think we should just keep going, see what happens. Instruction not found EA. That would make sense. So let's go back and check that the log around corresponds to what we expect. So we should have the test log somewhere here. Yep. And we're up to this JSR. So let's compare. I'm just going to put this over here. Oh, no, I'm not. Alright, it's this line. So C5FD is the memory location, 202D C7 is correct. It's a jump absolute, and nothing should be changed yet. And then after we execute it, we can't check until we've implemented the next one. That's a bit, yeah, okay, that's fair enough. So what's an EA? An EA is a NOP. Right, so we have NOPs. So let's look back at, not this, but yeah, here, and we should have a NOP operation. Now there's two of these web pages, and I always forget which one's awesome. This one's not doing anything. Yeah, no, I really like this one. So, hang on, let me just get this. Cool, sorry about that. So, where were we? NOPs. So a NOP is no operation, so we just don't want to do anything. And it's an implied indexing, which is going to be EA. So let's put that in. So let's get our base instructions up, and let's add a NOP base instruction. And it's just an instruction, and basically we actually just don't want it to do anything. Because the basic instruction will do nothing, right? Yeah, which we don't need to, so we don't care. And then the only thing that we'll need to do is to go back into our instructions class, and we'll need to add NOP with the correct indexing. So, which is immediate? No, implied. Implied. So implied addressing. I don't know what that's called, but I've definitely made that. Implicit, not implied. Oops. And from NOP. From NOP. Alright, and the identifier byte is going to be EA. Cool. So let's do that again. So we should make it to the next step. And we should be able to see that after we've done the JSR, we should be at C72D, which we are. So our jump has worked correctly. We should be getting in an EA, which we are. It should be a NOP, which it is. Nothing else should have changed. P should be 26. Alright, I'll need to look into that. Except our stack pointer should be FB, which it is. Yes. So what have we missed here? So our P actually changes from 24 to 26. So what does the P changing from 24 to 26 mean? Alright, well let's do 0x26 to binary. Let's see what happens when we do that. And just to confirm that that's right, so we start at 24. If we go to status, yeah, we've already got the 24 written there, right? Yeah, so what happens when we've moved to 26? I'm willing to bet that something has changed. Let's pad this out with zeros. So the difference is, well, yeah, it's too large obviously. I'm not very smart, but the 0 value has been set, which is set to be 1 if the last operation resulted in a 0 value. Right, so we're actually going to need to start setting some of these things, not based on the operation, but based on things that the CPU can figure out. So like whether did the last operation result in a 0 value, which is depends. So how are we going to do that? So that's probably going to come in, either the CPU or the base instruction class should return that. I'm unsure which one. How's it going to know whether the last instruction returned 0? Last operation resulted in a 0 value. Okay. Alright, well, let's see. Did the last operation result in a 0 value? So that's going to be our value, right? Maybe? It's not going to come through our side effects. The thing that we write is probably not important. Well, let's check it out. Let's check what the log seems to tell us. So it's telling us that the load x, that resulted in a 0. So that's load x, that this resulted in 0. That store x resulted in 0. That this resulted in 0. This resulted in 0. Huh. Alright, well let's go back to the CPU and let's look at the registers. Program counter, stack pointer, status register. PHP, arithmetic. Right, so we kind of want to be looking at the status flag behavior. This looks much more like what we want. Right, yeah. The B flag. There are only 6 and only 6 flags. Yeah, shit. Alright. Instructions that save or restore the flags map them to bits in the architecture period. So, one if the last operation resulted in a 0 value. So this is always going to be true past this point, right? Up until here. So what happened here? We had a load A and we loaded the value of 40. And when we loaded 0, it equaled true. When we loaded A, it equaled that. What does branch equal compare to? Beck. Actually, this side seems pretty good. This will probably tell us this side. Documentation. So what am I? 0. The monitor, blah blah blah. The 0 flag is set by all instructions where the result is 0. Yeah, okay. I mean, that's kind of useful. But I suppose I'm still confused about that. Bold of ending with the accumulator. Alright, so if the last operation resulted in a 0 value. So looking at the log, screw it, let's look back at the log. So a jump does not result in a 0 value. A load X does result in a 0 value. So what does a load X do? Let's look at our base instructions. It ignores memory address. And it's just gonna write the xreg to be value. So if this is value is 0, right. So what if we just do in instructions? Just down here we say return value. So the jump, and let's see what these things actually return once we call instruction dot execute. So our value is none, which is not 0. That's all we're looking at. So we don't set the thing. The next one, the value should be 0, so we should set it, yeah, which is what's happening here. And then from here on in, it should pretty much always equal 0. 0, 0, 0, 0. Wow, none. Bastards. So even a NOP is set equal to 0. Now you're confusing me. 65020 flag. Let's see what happens. I think the answer is probably going to be something along the lines of if some of these things are going to, depending on the addressing, going to implicitly return 0 or something. This flag is set to 1. Yeah, this looks like what we want. is set to 1 when any arithmetic or logical operation produces a 0 result, and set to 0 if the result. So any arithmetic or logical. Yeah, so it's not just going to be our value. It's going to be depending on what happens. God. Alright, let's ignore that for now, because it's going to get real tricky. Let's just keep going. So our status reg is wrong, which we know, but everything else seems right. Instruction not found. So instead of doing this one at a time, let's... Oh good, yeah, well it's going to take a while to get through all of these, but let's start doing them. So, store Y register. So do we have any store Ys? No. So let's create our store Y instruction, which I believe that we have. But nothing should use it. Yep. So pigsty, so sty. And here's the things that we want. So class sty 0 page. So it's going to use 0 page addressing with sty. And we want the identifier byte to be 84. I believe that's right. So I should be interpreting this. Yep. So that's done. Let's copy this, put that in here, put this in here. So what's the next one that we've got to do? 0 page x is going to be 0 page addressing with x. It's going to be 94. 0x94. And last one, sdy absolute. It's going to be 8c. Cool, so now it's pretty easy to create instructions. I'm just going to start doing it. The other thing I'm going to do is probably start splitting these up into like store instructions, because we have so many things. We may as well move some of them. So these can all be moved. Store A, store X, anything with an S in it. And we're going to move it to store instructions. I'm going to have a load instructions file, and in that we can chuck all this stuff. So this kind of move is pretty cool. Store instructions, load instructions, that's the file I want to put it in. Oops, missed one. Move it to load instructions. Cool. Alright, so store X is going to be store A. This is going to be store Y. So we've done store Y. Let's move up the stack to store X. We've got 0 page, which should be 86. 96 for 0 page Y. And absolute, which should be 8A. Yep, that's done. So stack instructions. These instructions are implied to have a length of 1 byte and have machine cycles as indicated. The pull one operations are known as pop. Oh my god. Okay. Pull. Ooh. It's P-U capital L. You are dedicated to this. Yeah. I try to be. Welcome back, Cutulus. Yeah, I went a while without streaming, so I'm back and trying to have some more fun with it. So I have no idea what these do, but let's assume that they do something useful. I'm not going to do them. All right, store A. So we've got a lot more store A's to go, so let's put them in. So we've got absolute, so let's do 0 page. So 0 page addressing with a store A, and that's going to be 8.5. Let's do 0 page with X, so there's going to be 0 page X, and the bytes are going to be 9.5. Absolute we've actually already got. I'll just move that down so it's in order, the order that we expect, and it should be in 8D, which we've done. Absolute with X, which is going to be absolute addressing with X. Did you resort to copy pasting? Well, I'm copy pasting these classes and then changing the small things about them. So I guess that's kind of resorting to copy pasting, but I kind of still like the way that it's set up, where I'm still constructing it and saying that it's made up of like a store A instruction with absolute addressing. So I am copying the code and then changing it to what I want it to be, but it's not like I'm copying and pasting a lot of redundant code. Yeah, or I hope. Let's look at addressing and let's see what can you do absolute addressing X offset? Yeah, I need to standardize some of these names. They're not great. This is a 9D. I'm definitely copying pasting the definitions of what these instructions are from the internet, if that's what you're talking about. QGIS? It's almost QGIS, which is a cool piece of software. Alright, so what's this next one? So we want to create a store Y, which is going to be with a Y. In fact, I'm just going to do it now. So it's going to be absolute addressing with X. What features will this have? I don't know. Whoa, that should be with Y. This is how bugs happen. I'm not quite sure yet, QGIS. Basically, getting it working is going to be a pretty big first step. So if I can get it to do that, I'll be pretty happy. And then once I'm there, I think things like recording and being able to do stuff like that are pretty simple. But yeah, find out when we get there, I suppose. Store A, store Y, blah blah blah. The identifier byte is going to be 99. Then this is going to be a store A with indirect X. Which is going to be indirect. Whoa, indirect X. Okay, it's going to be indirect this one. And it's not going to be 9D. It's going to be 8.1. If I could get Call of Duty to work, I'd be pretty impressed. Although, let's not rule it out until we get to that point. This is going to be indirect indexed. And it's going to have a thing of 9.1. Alright, let's keep going. That's all the store A is done. Subtracts with carry. Oh, that looks complicated. Return from subroutine, screw this kind of stuff. Let's find some nice easy loads. Nops, I can do nops. Load Y register. Let's finish off our loads as well. So LDA. It might there might be shooters on the NES, I guess. I don't actually know. Holy crap, there's a lot of instructions. I suppose we knew this. Alright, and last but not least, load Y. So, load Y. Let's get it in there. So we've got immediate, and it's A0. So we've got that down. We want LDY 0 page, which is going to be 0 page addressing. It's going to have a thing of A4. Then we want load Y lady 0 page X, which is going to be 0 page addressing with X, and that's going to be a B4. Did you ever play Double Dragons? It was lit. I did not. I pretty much played Super Mario Brothers and Duck Hunt and that kind of stuff. To be honest, my NES gets 120 FPS. I play Minecraft on it all the time. Even running Minecraft would be pretty impressive, to be honest. I don't think we're going to get to anything too impressive performance-wise, but that's perhaps less the point than trying to have some fun with it. As much fun as you can have making an emulator, I suppose. B4, LDY. Alright, so what else we got? We got LDY absolute. Nice. And we got load Y absolute X, which is going to be absolute addressing with X. Now this is going to be B4, AC, BC. Nicey, nicey. What about Contra? Yeah, that's true. I did play Contra. I actually played it, oh man, what's that? Someone just released a Super Bros or something. It's like a really modern, well, obviously modern, but it's on Steam. It's like a platform shooter, which was heaps of fun. What you making? Jeezker. I am making a NES emulator from scratch using Python 3. So basically at the moment I'm working on emulating the CPU. So I'm creating arduously one by one all the instructions that the assembly instructions that the CPU can understand. Let me know if that makes sense to you, because I can explain further. Man, what is that game? Super Awesome Bros or something? Damn, I don't know, it was a heap of fun. Alright. So we've got load Y is done. So let's do load X. So we've got load X immediate, which is A2 and immediate. Yep, so we've got that down. We want to have a 0 page. 0 page addressing. It's going to be A6. Load X, 0 page Y. It's going to be 0 page addressing with Y. It's going to be A6. Nope, it's going to be B6. And why do random people come in and programming screens point out every flaw? Yeah, look, I've had plenty of constructive comments To be honest, though, I probably get more out of people coming in nitpicking though than not. I've had some really helpful people stick around and like actually explain what the hell I was doing wrong, especially when I was starting out. Like, didn't even really understand how bytes and hex worked in Python. And Danny's been pretty awesome in kind of doing some stuff at the same time. But for every one of that, you do get, yeah, exactly. You left your stove running in div. Probably the main one is just like the architectural decisions I'm making, which I admit are probably questionable. So it's all a bit, yeah, it's all probably valid. I'll give it that much. I don't know. People like to come in, see what's going on. I think if I was doing something I felt a little bit more confident about, I'd be less worried about. I'd be more like, frustrated at people backseat coding. But to be honest, I don't really have any idea what I'm doing. So sometimes I do actually leave a stove running in my div. BRB, fair enough. This should be a load absolute Y. Yeah, absolute addressing with Y. And it should be BA. Cool. One thing I'm going to do here is make sure that we don't have any colliding things. So if instruction in self.instructions, duplicate instruction identifier bytes. And the reason that I'm going to do this is in case I make a copy paste mistake, which I probably will, and forget to update something, it will just catch it for me. Cool. How about load A? So we've got immediate, indexed, indirect. Yep, 0 page X, absolute Y, absolute X. How many? 1, 2, 3, 4, 5, 6, 7, 8. How many are there? 1, 2, 3, 4, 5, 6, 7, 8. Nice, okay. Jump to subroutine we've got. Hell yeah. Jump we've got, but we've also got 2 modes for jump. Alright, so let's find our instructions. Let's create a jump instructions file, because there's going to be a fair amount of them. Jump instructions. JSR. So jump, we've got jump absolute, and we also wanted to jump indirect. Indirect addressing. Yeah. Oops, and what's the identifier bytes? 6C, cool. 6C, 0x6C, because otherwise it's not a thing. Alright. Instead of calling this instructions, whatever. This is just our catch-all thing for everything else. Increment memory, I have no idea what that does. Alright. Flag, processor, abstractions, EOR, decrement, compare, break, branch, and ADC. Cool. So the rest of these are, I haven't made yet, so let's not worry too much about them. Now, one thing I wanted to look at was if I search for LDA here, see what memory does this address. So this is saying that it affects the N and the Z register. So if we go back to our status thing, status here, our N and our Z, I presume that's, oh wait, is that negative, an overflow? Oh, their status thing is in a different order. That's not good. So what it's telling me is it affects 0 and negative. Oh, so negative. So we do have signed things. Holy crap, that's a big revelation. Alright, MDC. Yep, so C is carry, I is interrupt, D is decimal, V is overflow. Okay, so we do have all these operations implemented correctly. They're just in a different order here. So what this is saying is load is memory to A, and these are all the different types of addressing. Oh, hey, this has it as well. It's immediate. Is that how you spell immediate? No way. Immediate. Yeah, okay. This cycle stuff worries me because I don't know what it means. I presume we run the specific clock speed and they take a set number of cycles to finish. But I don't know if we run things concurrently or if we just run them like one after the other. Or what, yeah, how that matters. This byte starts, I suppose, I've got implicitly in the addressing and the opcodes. Cool. Let's keep going then. So it can set the N and the Z bits. So I might actually copy this and put this into LDA because this is probably going to be useful information to have later on. And I presume all loads are the same. Yes, even, yeah. So let's just copy this shit and put it here. Let's copy this shit and put it here. Alright, so now that kind of gives me a bit of an indication of what's going to need to happen for the status registers later on. Let's keep going on them. Let's find out what store. Yep, okay, so store does nothing to any of the registers. Right, so this is how it's going to work. So it's not going to write them. It's not going to update them unless it has a plus on one of these things. So this is really good information to have. Set bit. Looks like SEI. Right, in the status reg. So this can actually set any of the bits, one presumes. Alright. What's our other shit that we got going here? Nop. Let's presume that a nop does nothing. But we should probably check that. Nop. Nop does nothing. That makes sense. JSR. Does the JSR do anything? No. Does the jump do anything? Probably not is the answer then. I would think. Jump around. No, doesn't do anything. Nice. So this is how we're going to know. So the only things that change these N registers are going to be, this 0 register and this negative register are actually going to be our load wires. So that's why we set things to 26 and then nothing actually changes for a while because, yeah, nothing happens. So what does LDX do? So there's kind of going to be this intrinsic property of an instruction which is going to tell us what status registers it can update. Now probably the easy way of doing this is in load instructions to manually set the 0 register and the N register. So I'm going to do that. And in fact, I'm going to do it this way because why not? So we're going to make a load instruction. Bleh. It's going to do that. Yeah, and it's going to set the areg. Now instead of setting the areg, it's going to set the we'll create a method called like class dot, I don't know, reg to set. And we'll just say, yeah, it's going to need to be a method, isn't it? And then we can't just say that. We're going to need this returns a value. So reg to set equals this. Reg to set. Oh, wait, what? cp.areg. Whoa. Yeah. All right. Let's say this is just going to write our okay. So set the n and the z regs. Potentially we might move this code later on to the CPU, but for now let's just write it here. So if value equals 0, CPU.statusReg dot how do we set this shit? CPU.statusReg dot interrupt bit. Okay. Dot 0 bit status. CPU dot what the hell? Well, that's not how this thing works anymore. Status reg dot interrupt bit equals true. Yeah, it's actually going to be status bits dot bits. Wait, what? Status dot status dot status types. Right, okay, so I half implemented this. So really what this should be is the status reg dot bits class dot bit is going to equal true. Unresolved attribute reference, yeah, whatever it's set in my base class. And this is going to be the same, except it's going to set to false. Cool. Alright, fair enough. So down here in the loads, we're going to do cpu.statusreg.bits. So the 0 bit, God, which is a status dot whatever, you know what I mean. Status carry. No, I want the 0 bit, and I want to set that to true. True. Else false. Now we don't actually need to make that a true or false, do we? And if we can just say that. So the CPU 0 reg is set to whether the result equals 0, and then the what was the other one? The n negative set to bit 7 of the last operation. Value less than 0. Alright. One of these things is going to come back to bite me. Now, here's the interesting thing. We could do this, but we only wanted to do it on operations that are that set the right thing. So I kind of want to make it by default, not write any registers, not do anything, but then have something where it can say, hey, set the N or the V or the Z or whatever based on the result of this. Yeah, so let's do that. Let's move this code into the status reg. Let's take in a instruction and a value. Right, so I kind of want to do this. So this is going to be a c.cpu input CPU as C. Instruction is going to be of type instruction. I have to do this weird importing due to the circular imports that typing creates in Python, which is a bit of an issue at the moment, as ins, and a value, which is going to be an integer, we presume for now. Can't find reference instruction. Cool. So let's update the status. Whoa. Based on the instruction attributes and the value calculated. So we only want to update the 0 reg. This should be the carry reg or something. What's the n reg, the negative reg? So if the instruction dot let me think about this. So if it sets the 0 bit, then we want this to be updated. And then if the instruction dot sets the negative bit, we want this to be updated. Alright, so what things are going to set the negative bit? So for LD, right, let's go to instruction. Let's say that by default, everything returns 0. So sets 0 bit equals false. So we're going to make these attributes of the instructions about whether they affect this kind of stuff. And then down here, we can just say that a load is going to set the 0 bit and the carry bit, the negative bit. Words, alright. It's pretty cool. Let's make that inherit from LD. LD and LD. Nice, and everything else is false, doesn't set anything, except these ones which set it manually, so we don't really care about that, to be honest. Done. Okay, and now all we need to do is call this update method. Actually, this can just set itself, doesn't need to go through the CPU. Alright, therefore it doesn't need to be passed to CPU. In fact, we can probably get away with doing a normal instruction import here. So let's call that. So we've incremented the PC reg. Value equals that. So we execute it, and then we want to self.status reg dot update with the instruction and the value. Give me a second. I'm going to be right back. Alright, I'm back. Sorry about that. Yeah, I'm kind of happy with this. So I think this will make our lives easier. Expected type instruction got type none instead. Okay, what? Instruction is not type none. Instruction is type instruction. Yeah, sure. Alright. Test run. Let's run it again and see what we get up to. Instruction not found for C. What is self.instructions? Only 3 things inherit from instruction. This is one of those things where I've moved everything into different files. And I need to import them before I can find them. So when I import instructions, we're going to import jump instructions, load instructions, and store instructions. I think that's all I've got. I really should put these in a folder. But they'll do. They'll do for now. As jump instructions file, load instructions file, and store instructions file. Cool. Let's keep going then. How many instructions do I have now? 37. Oh yeah. Alright, instruction not found. 3.8. 38 SEC implicit. Yep, so let's set all these set and clear things as well. So status instructions. So we've got SEI. We also need an SEC. So we need a sec, which is going to be 38, and it's going to set the carry bit. So that's done. SEI 78 and set the interrupt bit, which we've done. SED, which is going to set the decimal bit. Which is going to be F8. Cool. Set our clears, so we've got clear decimal. Holy crap. So we just did set decimal, right? Yeah, so we've got clear decimal. Let's do CLV. Just going to overflow. It's going to be B8. We've got clear decimal. Got 2 more to go. So we've got CLC, which is clear the carry bit, which is going to be 18. And we've got CLI, which is going to be 58. Just going to clear the interrupt bit. All right. Let's call these set status instructions. Let's call these clear status instructions. Alright, we've done them. That's good. The interrupt flag is used to prevent SEI or enable CLI multiple interrupts. Yeah, okay. The decimal flag. Oh god, arithmetic is carried out in packed binary coded decimal. This flag is unchanged by interrupts and is unknown on power up. The implication is the CLD should be included in boot. Holy fuck. Alright. Well, we ain't gonna read that, are we? Alright. What are we up to? B0. How many instructions am I getting through? Not that many. B0, alright. Where am I? B0. BCS. What is a BCS? Branch on carry set. Ah, so we're doing a branch. So we're branching on C equals 1. All branches are relative mode and have a length of 2 bytes. Okay, so, right, so we're going absolute. No, absolute length of 2 bytes. So it's relative, so you can only get 256 bytes in either direction. No, 128 bytes in either direction, I suppose. And they're in, yeah, see the program counter. Whoa. Once it has the opcode, it increments the program counter by the length of the operand, if any. So actually this PC reg, yeah, that makes sense. Alright, so where was I? BCS, somewhere. Branch on carry set. So this is going to be a jump operation. Branches, branch operations, branch instructions, I think is what we called them. And we're going to do branch on c equals 1 relative. Where does this relative thing come from? Rel. Do I have a relative? Bit 7 in signifies negative offset. Yeah, okay. Do I have a relative addressing thing? Because that would be handy. Oh, to do, signed. It is signed. I do. Yes, that's awesome. Can only jump 128 bytes in either direction. Hell yeah. Off by 1 error. That'll never happen. Get the program counter. I've never had a bug before. Cool, so this is after we've incremented, which I believe is what we want. Offset by the value in the instruction. Byte order little. Oh, not sure about that. All right, so let's do it. So, what is it called? BLS, BCS, branch carry set. BCS relative. So it's going to be relative addressing. BCS. So all these B's, all these branches are just gonna, they're all relative, right? Yeah. So let's create like a generic or a base branch instruction. Branch. Alright. Branch, and they're all going to set on branch on carry equals 1. So they're all going to have a null set of things that they affect, which is always handy. What are they going to do? So they're going to branch, which is going to be a jump, when some condition is met. Right, so let's do the same thing as here. And let's say that the PC reg is going to be the memory address, and we'll get that using relative addressing. But we only want to do this if a certain condition is met. And then what is that condition? That condition is going to be different, and it's going to depend on BCS up here. It's going to define not only an identifier byte, but it's going to define what we want to split on, which in this case, branch on c equals 1. Yeah. So the branch is actually just a jump instruction. This is where things get cool. Branch is actually a jumper with a condition. I knew this. And what I actually wanted to do is just to inherit from that and then just say if CPU dot status reg dot bits No, I'm going to do it this way. So branch is going to inherit from jump. It's not going to have any of this crap. And it's actually if CPU dot status reg dot bits, and then let's define a bit. Where's status? Class dot bit equals true. So we only want to do this. We only want to branch if our condition is met, and we're presuming that it's going to come from a condition in the status reg. And so therefore all we need to define in the jump instruction is the identifier byte and the bit that we want to jump on, which is going to be the carry bit in this particular example. So BCS is just going to jump on the carry bit. Right, that's pretty cool. Hey. Things are getting a little bit nicer. I'm just going to quickly try and resolve this one last time. Sorry, give me 2 minutes. Right, we are good to go. Alright, what's next? BCS. Alright, let's implement some of our other branch instructions while we're doing this. Branch on carry clear, branch on carry set, branch on result 0. Okay. So that was branch on carry set. Let's do branch on carry clear. Yeah, here we go. This site has a very nice summary of them. Although it doesn't appear to have, wait, branch on carry set. So branch on carry set thing was 20. Oop, I have no idea where I go. Oh, that's a copy and paste error. Alright, so branch on carry set is B0. 0x B0. Yeah. 0x B0. Nice. Okay. Then, so that's branch on carry set we've done. Branch on carry clear is going to be the carry, but it's also going to be, alright, so some of them are going to be, this is actually going to inherit from branch. And we're going to have clear, overflow, plus, minus. Yeah, so it looks like, what's BPL? Yeah, okay. B&E. Yeah, okay. So they're all going to be set of this stuff, and we're just going to have, clear ones and we're going to have set ones. So we're going to have ones that are, so branch. We're going to have branch on clear and we're going to have branch on set. which are going to be very similar, except there's going to be a not in here. Yeah, whatever. Branch, clear, branch, set. So set, do it if it's not, clear. So set if it is set, jump. Clear if it's not set, jump. And in fact, I can just do super. Because otherwise, why am I inheriting from jump? So BCC, so these things are actually just going to be inherit from branch set, branch clear. Okay, so branch on carry clear, which is going to be 9, 0. Branch on plus. So branch on n equals 0. Which is going to be, yeah. So what's it called? Alright, so let's go branch on plus BPL. Branches on n equals 0. So branches on n being cleared. So it's a clear branch. And we want the negative to be 0. And that's at 10. Okay, yep. More instructions. Alright. And then we want minus, which is BMI, which is where we want the negative branch to be set. And that's at 30. Is that right? BMI. BMI branch on n equals 1. Yep. Yep, okay. And these are all from jumps, and jumps are relative. Okay. No, branches are always going to be relative. I really should put these into the same thing somehow, because the only difference is an if versus an is and not. Yeah, good. Yeah, look, whatever. It'll live. Alright, so BMI we've done, which was 30. BVC, let's do. BVC. Branch on overflow clear. So branch, so it's a branch clear operation. It equals 50, and it's on V. No, what's it on? V equals 0. What does V mean? Overflow. Sheesh. And then we've got BVS. Should be coming up next, which is going to be a branch set. It's going to be 70. And it's going to be sitting on overflow, yep. We've got B and E and, yeah, someone else. Okay, so we got branch not equal. So which one is B and E? Branch on result not 0. Whoa. Branch on 0. How does that make any sense? Oh, okay, so we branch I'm just going to check that with this thing. Branch on not equal. Huh. Be equal. 0 set. Okay. So this is going to be a branch clear on the 0 flag. And be equal is going to be a branch set. I do not make the rules. Alright, and this is going to be D0, and this is going to be F0. The 0, B and E versus BQ. BQ is branch set. Okay. So let's put this into branch sets. And then branch clears. This is branch clears. Can go down the bottom. Branch set, branch set, branch set, branch set. Okay. Kate branch set. Branch clears. So we've got 3 branch sets. 4 branch sets. 1, 2, 3, 4. 1, 2, 3, 4. Alright. Cool, we get a lot further now. Way further, even. We still definitely have a bug in our addressing code, which I need to fix up. But, you know, still got instructions to go. Alright, instruction not found, 24. So, back to the top. Back to the top. 24-bit. What is a bit? Bit test. Yeah. So the PC is 16-bit. You nearly got me, PC. You nearly got me. Test bits in memory with accumulator. Bit 7 and 6 of operand are transferred to bit 7 and 6 of SR. Oh god, I'm just thinking my byte conversion doesn't take into account whether something is signed, it just mods it at 256. Oh, that's gonna be a bug. That's to do signed values. Ha 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 ha. Alright. Bit of an operand transferred to bit 7 and 6 of SRNV status register, negative overflow, and the 0 flag is set to the result of the operand and accumulator. What the fuck? So A and M. Right, so the accumulator is ANDed with memory. Bit 7 and 6 of the operand are transferred to 7 and 6. Right, so that's the status register, and then ANDs things sets the 0 based on the ANDing of the operand and the accumulator. So presumably the operand it's going to be testing these bits or something. Holy crap. That's blowing my mind. Not ready for that. I think I might wrap it there. I think that's done me. That's ruined my brain. Oh yeah. Bits. Cool. Anyway. the real question is whether I keep going on other instructions that aren't that one. Actually, you know what I'm going to do? I'm going to try and fix this addressing bug. I always talk about fixing it. Alright, addressing. So the bug is down here. Whoa. The bug is down here to do bug with offset getting reused. So the issue is we're using a lot of things that inherit from the same kind of structure and their methods are colliding. Which is just some poor design. So really the problem here is that this indirect addressing tried to do things a bit too smartly. So it tries to use absolute addressing, and that's fine. And so it gets a memory address, and then it's trying to... So what indirect addressing is doing is getting a memory address, finding what's in that memory address, and then whatever's in that memory address, turning that into a new thing to look at, and then returns the value of the thing that's in that indirectly, that second memory address, which is kind of around the point that my mind just explodes. So this is how we do it. So we got the address from absolute addressing, which is our normal mode of addressing, and then we're going to turn that into a from bytes and then get the offset. So I think this class.getOffset is where we're going wrong. Almost certainly. So we definitely want to get the address, the original address we want to look at, and we want to get those things, we want to return that, and then we want to do a bit of an offset. The problem is that this class.getOffset method is getting used in up here, so we override it. So I think the problem is that we shouldn't be using it here. So when we do get address in indirect base, this is fine. It'll get us this fine. This will work fine because zero page addressing with X, when we call super.getAddress, it'll call zero page addressing with X, which will return the thing with the offset. Oh god. To do check for overflow, this could probably... Oh no, this looks up an absolute memory address in the first 256 bytes. Okay. Sure. So, yeah. So the offset works here, and this will get it this. The problem is here, we get with zero page addressing, indirect base, and then we want to add the Y-reg offset. So instead of doing this, adds the Y after the indirection. Let's just do it manually. So let's just call our parent getAddress method super.getAddress. Holy shit. CPU data bytes. And then this will get us the thing from indirect base with zero page addressing, and then we want to add the Y-reg. CPU.yreg. This is a bit of a dodgy way of doing it, but whatever. But the answer is, so we just look it up using zero page addressing, and then indirect that, and then we're going to add the Y-reg after we return. Whereas this one, we're going to look up the zero page with X, and then we're going to use that to do indirection. And then this one just doesn't normally. Oh man. Bug fixed, but mind blown. Well, maybe bug fixed. Yeah, 24. So this is the same one. So we're getting a this bit comparison. Let's go back and check that we've kind of implemented everything reasonably well so far. Check that our status stuff is getting updated. So what Danny was saying was I probably should come up with something that can parse this and just do some checking against my values to these values. based on the size of this log, I'm gonna go ahead and say it's probably worth my time. So .web archive. Okay, can I? Sure. Control A, Control C. Yeah, let's just put it in here. So NesTest.log. Yeah, that looks around right. These spaces. Yeah. Right, so there's at least 2 spaces between each section. But then that's, oh my god, this is terrible. Alright. Let's go back to our main. CPU.runROM. So the CPU probably shouldn't know. So this is what Dan was talking about, was how you're going to make the CPU know. The CPU doesn't really care about the test log. Yeah, interesting. Maybe this is probably a step too far for today. Alright, let's leave it then. Let's just walk through what we've done today. So, made some names consistent. I think this should be correct now. We know that relative addressing is signed. Off by 1 error. Oh god. We fixed up the bug with the get offset being reused. So now it's not being used in this, and we just manually add it on at the end here instead of using this Y-Reg offset. That's cool. Base instructions, we've added more things. So now instructions by default, we're documenting what things they modify, what registers they modify. And for those ones that do modify things, we add on a sets 0-bit and a sets negative bit or whatever bit to be true. And then that way we can use the CPU to know which things it should update. We've created a lot more. So we've added load Ys, load X's, jumps, set bits. Set bits work now instead of just setting the interrupt bit. Yeah, so a lot more instructions. The CPU only does loading instructions once. It's a bit smarter about setting memory. Manages the stack size a bit better. It might be pushed out to something later on. Yeah, that sounds sweet. Generic instructions. So the 0-bit being false. Yep, so this is learning what to modify. Returns the value so we can do comparisons when we're doing the 0-bit and the negative bit. Simplifies the memory. Started doing some of this int short conversion. It's probably going to be helpful in the long run. Added more NOPs, more set and clear instructions. Added all our jump instructions, including branch instructions. Branch. So we can say that we are either set or clear and then what your bit is. Load instructions are all implemented. Memory owner, whatever. That's fine, we just fixed the bug to do with how it was actually setting shorts as opposed to bytes. It's what happens when you set the program counter. Status now updates itself based on the properties in the instruction. Store instructions and some refactoring. One last thing I might do, let me think about this, is say that spreg, not spreg, pcreg is 16-bit, or 2-byte, which is, yeah, pretty non-documented. in the rest of my code. Cool, and the reason that is because even though it's an 8-bit CPU, we have a 16-bit address bus, which means that we can access 65 kilobytes worth of memory as opposed to just 256 bytes, which is a pretty small amount. Cool. So we load all our instructions and stuff. Let's just do it. Let's move all these instructions things to a folder. Yep, that looks good to me. You can't inherit from generic instructions. Can you? Nope. What about base instructions? No, these are all basic. Cool, so how many instructions do we have? Oh, no, CPU stuff disappeared. Oh, it got me. So import instructions dot jump instruct. The reason we have to do this is because of the funky way where I'm finding out what instructions are just by iterating over base things of the class, instruction class. So we need to import the files where everything is defined. How many instructions do we have now? Probably around 40. 50. How many instructions are there? 151 or something? Holy shit. It's not a quick process, this one. Oh well. Third of the way there. Plus any illegal instructions, but we're not going to think about them at the moment. Yeah. Let's say that that's a pretty good place to stop. Code appears to be working. If I run this through, it should stop at 2.4. Yep, and we're getting around, I don't know, what's that? Maybe around 50 instructions deep. It's pretty sweet. CPU status. Oh man. Up to 50 instructions. Minor addressing. Cool. We're going to add a tag as well. And then we're probably going to end up episode 6 push tag. And we'll just check that this has in fact worked out for us. 24 seconds ago. Perfect. 5 releases. Should now be 6 releases. Yes, there are. That's awesome. All right. I think on that, I'm gonna finish up. Thanks for watching live, and the people that are following this series on YouTube. It's awesome to do this with people, and yeah, have a good time. Thanks for coming along, and I'll